Good afternoon, learners. Welcome to the teleconference program on conducting by Department of Physics, Dr. B.R. Ambedkar Open University. I am Dr.E. Vijaya Ushasree, Department of Physics, Dr. B.R. Ambedkar Open University. So, today's our teleconference topic is nanoscience and properties of nanomaterials. So, this topic is useful for third year 6th semester learners as well as MSc students also. So, this program is duration of this program is total 60 minutes. First 50 minutes our experts are here to discuss about today's topic, and last 10 minutes that is completely learners time. So, learners interaction time, that is so learners whatever you have doubt today's topic, you have to express your doubts to contact for this teleconference program. Call upon 040-23-680-456. Again I am repeating this number 040-23-680-456. Now, I introduce today's our esteemed experts and experienced experts. First of all, I have to introduce Dr. Maduri ma'am. She is assistant. Namaskar. She is assistant professor, Osmania University, Hyderabad. So, another expert is also with us, Dr.S.E. Naina Vinodini ma'am. She is associate professor, Government City College, Hyderabad. So, thank you madam joining us today's teleconference live program. So, this is before that we have to move for this discussion part. We have to know that what is a nanoparticles and what is the synthesis of nanoparticles, and what is the bulk material and top down setup and techniques. All these things we will discuss with our today's experts. First of all, I have to ask to Maduri ma'am. Maduri madam, what is a nano and what is the scale of nano, and what is the synthesis of nanomaterial? How we synthesize these materials, please?
Actually, we know that all materials which we are seeing is bulk materials, and what 10 to the power of minus nanometers, centimeters, units, particles, whatever it is there, those particles will call nanoparticles. Okay, 10 to the power of minus 9 centimeters, nanometers means you know that 1 to 100 we already regularly seeing, then 1 to 100 nanometers we can call it as nanoparticles. Nanoparticles preparation and synthesis, preparation means synthesis techniques, and how to confirm this is nanoparticles, that is characterization techniques. These all comes under nanoscience. Whatever the nanoscience we are calling it is, we are completely studying about nanoparticle preparation and nanoparticle characterization, and what are the properties are available for nano. Okay, this is overall nanoscience which we are discussing properly. Okay, these nanoscience particles will be classified into 3, 0D, 1D and 2D. Okay, 0D means which are and 0 dimensions are in not in nano, and means 3 dimensions. Any particle or molecule or atom we can describe by 3 dimensions only. Okay, all 3 dimensions are in nano range is 0 dimensional nanoparticles. 0 dimensional nanoparticles, for example quantum dots, these are all comes under 0 dimensional nanoparticles. And 1D means 1 dimension is not in nano, means only 1 dimension is bulk size, and other 2 dimensions are in nano range, means other 2 dimensions will be in 1 to 100 nano range. Those will call 1D nanomaterials, 1 dimensional nanomaterials. For example, these are, you know that nanorods and which are in cylindrical shape, we can call it as 1 dimensional nanoparticles. And 2D means same simple, we can remember that 2 means 2 dimensions not in nano range. అంటే any in 3 dimensionals 2 are not in nano means 1 in nanometers. Means 1 dimension is in 1 to 100 nanometers, that we can call it as 2 dimensional nanoparticle. For that examples are nanosheets, nanosheets. Okay. Then next, what is the importance of nanomaterials? Why it's became most important and research giving more important in nano means while the bulk material reduced to nano, the properties will be changed, and whatever the properties are there in bulk may not be in nano. Okay, that will be perform in different properties, and when it reduced to nano, surface area volume will be increased. While surface area is increasing, interactions will be increasing. Where interactions are increasing means there possibility of n number of properties. That's why nano became more important. Okay, example, energy materials are nowadays prepared by nano only, most important. Okay. Next one, the synthesis of nanoparticles will be divided into 2. One is top down method and another one is bottom up method. Top down method is simply breaking down of size. Simply we can define it is breaking down of size of the particle, and bottom up method is building up the nanoparticle, and we are preparing nanoparticle by itself. We are not breaking down the size of the nanoparticles. And the top down method, it has 2 types of there. One is physical synthesis and chemical synthesis. Slide physical synthesis and chemical synthesis. Physical synthesis, it has
Madam kitchen. So what is the vapor disposition of this? Can you explain about the synthesis of sol gel method?
That is one of the chemical synthesis of nanoparticle made, one of the method of chemical synthesis, sol gel method. Then while coming the explanation different methods, I will explain about sol gel method. First we will go through the physical methods which are available, and most prominent method we know that ball milling method.
Okay, high energy ball milling method is one. Okay.
One most prominent method which is available and plenty of availability in labs. Okay. Ball milling method, they can provide steel balls to reduce the size of the nanoparticles, and whatever the compound is there, with that compound balls will be there. While rotating the mill, the balls is also rotate with that. Then depending on that, the size of the particle will be reduced. Okay, this is depending on time to grind, 1 hour 2 hours, depending on that size will be reduced. And simply we can say that it is an physical method, and we are applying a energy to grind that mill, whatever it may be, then it will be reduced to size. These physical methods whatever is available, those are physical energy is more, that's why the drawback of those methods. Next, physical vapor deposition. Simply it one source will be there, we can give energy to evaporate that source. Okay, these evaporated material will be formed in a substrate. From that substrate we can collect our nanoparticles, that is physical vapor deposition method to prepare nanoparticles. This is ionization deposition, means ions will be evaporated.
Okay.
Previously what we did, the whatever the compound is there, we can evaporate that, then nanoparticle, here ions will be evaporate.
Okay.
Ion, that is the instrument which we can use for ion deposition. Ions will be deposit on the output. Okay. Then sputtering means, simply sputtering meaning is pull out something. Okay, here we are pulling out our nanoparticles by using that. Then previously we are using energy to evaporate. Here we are using laser beam to evaporate our material. Then the nanoparticles will be, whatever the gases are forming, that will be emulate with Ori office which is there at helium.
Next.
And next one is hybrid nanoparticles. nanoparticles, nano composites means which we can say that any one of material, and in a composite any one of material will be nano, we can call it as a nano composite. These hybrid nano composites will become more important by these technical era. One of the nanoparticle embed in a bulk material. These nanoparticle will provide whatever the characteristics we need for the instruments, whatever it may be, any instrument depending on the condition of your instrument, electronic instruments, energy storage applications, whatever it may be, we can prepare a hybrid material by using nano to get such characteristics which we want. Those materials will call as hybrid materials, because we are forming a compound which using some of the materials. In that chemical synthesis, most important and familiarly most we can use sol gel method. Sol gel method, first we can prepare a solution, metal ionic solution. For that solution we need to maintain a pH. For pH we can use some of the cases we can use ammonia to maintain the pH. Then we can wait for condensation process. Then after condensation process, that solution in under the solution, whatever it may be, under the beaker, the gelatation will be formed and a gel will be formed under that. Then we can after getting that gel, we can keep it hot air oven.
So
then we will get
for the sol gel method, we are getting some gel. What we are adding the chemical of for that preparation of gel? Can you tell me that?
Most probably
type of
we
chemicals?
Most probably available one is citric acid. Citric acid can use to form a gel. We can prepare whatever the compound we need, which ions we need, nanoparticles, we can prepare a solution and then we can add this citric acid. Then we need to maintain a pH for that solution. Then pH maintenance, then we can wait for forming of gel and condensation of the solution. Then after condensation we can get that compound, whatever the gel form is there, then we will
next.
This is a procedure which we can use. And one of the method, chemical method, CVD, chemical vapor deposition, we can use a chemical to deposit. A chemical will form to vapor, vapor will form, in vapor nanoparticle will be there, that vapor will form on one layer. One example we given for carbon nanotubes. From chemical how it is evaporating and how that carbon nanotubes are forming, in that we can form that.
This is the process for that
chemical vapor deposition. Another one is electrical one. In sol gel method, what we did, we need to add some of the chemicals to get that gel form or whatever it may be, nanoparticles. We need chemicals to reduce the size of, then we used only citric acid for gel form. But here what we can do, just we can form a electrolyte solution, then keep the electrodes in that solution. Then we can apply DC power supply. When we apply the power, automatically the ions will be dispersed. Whatever the dispersed ions are there, those will form on anode. Then we can get your nanoparticles. That is one of the this is spectros. And then here now onwards, and up to previous we discussed about what are the synthesis process are there to prepare a nanoparticles. అంటే nanoparticles తయారు చేయడానికి ఏమేం పద్ధతులు ఉన్నాయో మనము ఇప్పటివరకు చూసినాం. నెక్స్ట్ అసలు నానో పార్టికల్ తయారైందని చెప్తున్నాము, బట్ వీఆర్ సేయింగ్ దట్ ఇట్స్ నానో పార్టికల్, బట్ వీ నీడ్ టు కన్ఫర్మ్ ఇట్స్ నానో పార్టికల్. హౌ వీ కెన్ కన్ఫర్మ్ ఇట్స్ నానో పార్టికల్ మీన్స్ డిఫరెంట్ మెథడ్స్ ఆర్ దేర్, XRD, UV, IR, SEM and TEM. These are all comes under spectroscopy techniques.
So whatever we have to divide that characteristics of nanoparticles are there, these equipment we will use like a SEM, TEM, these these are the techniques we are using to divide that nanoparticles. Is it correct, ma'am? Yeah. So what is can you explain any XRD about how we synthesize that nanoparticles to divide from the bulk particle?
XRD is one of the characterization technique to prove that what is the average despacing size. Means XRD we already know that BRAOU's law and shear crystal structure. And shears formula, we know that Debye shears formula, D is equal to K lambda by beta cos theta.
Next.
Okay, K is, oh madam, explain. Okay, whatever the average size of that crystal despacing will become, which graph we are showing that is crystalline material. Okay, if it is amorphous material is there, we will not get the peaks whatever we are seeing. Okay. Then next.
So what about UV equipment of visible spectroscopy? Can you tell
UV
me that
visible
how we will divide that?
spectroscopy, it will be a range of below 200 is, we can call it as near UV, then above 400 to 800 nanometers, 800 nanometer, we can call it as UV visible range. Okay, UV visible range means what we can, when we keep a solution in front of the UV rays, then one of the ray will be absorbed in it. Whatever the absorption is there, we can give a reference material to get that how much absorption is happen. Okay, depending on that absorption, it will give the peaks whatever it is there. Okay, sometimes these peaks will be shift. Redshift means when it is longer distance to the UV range, that will be called redshift, and if it is shorter shifted to shorter distance, then it will call as a green shift. Okay, this is example UV. Okay, these are the prepared samples. We will get UV like that peaks. Okay, depending on that peak, we can confirm that which material is there in that.
Okay, in
that
IR
wavelength.
In IR spectroscopy, madam, how we
IR will give the whatever the bonds are there in that. Okay, as we know that CO bonds are there, OH bonds are there, NH bonds are there. And what are the bonds are there in our prepared material? We can get from the IR spectroscopy. And we know that IR region, whatever it is there, mid region and far region, from that graph we can know that
we will find that nanoparticles. Spectrum. In that spectrum only we will find that
IR we cannot say that it is nanoparticle or not. We can say that which particle is there in that and which material is there in that, which compound. If you are getting stretching band and bending bands, vibration, when it is vibrating, that OH stretching band or OH bending band or whatever it may be. If it is like this, it is stretching band. If it is like this, it is bending band. Okay, and those will be given by IR. Okay, we could not say that by IR it is nano or one. Which compound is there in that, we can say that.
Okay.
Stretching and OH.
Next.
Up to skip JC and this is the process for IR complete. IR and madam okasari back. How we will get that stretching and bending bands, and depending on that we can expose the sample with IR. Okay, IR radiation. Then what will happen, we can get the transmittance. How we can get the transmittance means, we will give a reference source to the instrument and our sample will be there, and whatever the difference is there, we will get that transmitted one. Then I by I naught is initial incidence. I means whatever the transmittance is happened, by that we will get the how much transmittance is happened. By that peaks we can say that wave numbers, we can say that how it is a stretching band or bending band, or depending on that wave number we can find that.
Only that purpose we are using this IR spectroscopy. Okay ma'am. Next.
It is a SCEM. Up to here we said that a sample and whatever it is there, it will be absorption or transmission, either UV and IR. Here SEM will be structural property. Okay. It will, and by the SEM we will get, under scanning electron microscopy, by the SEM we will get only surface morphology of the material. And maybe it is spherical, it is rod, or it is flower, or depending on that we can confirm by the SEM. Okay, in SEM what is there, we will not expose the sample to the any light. We can expose to the electron gun. Okay, and electron gun will release the electrons. Okay, these electrons will embedded on our sample, then where we can focus, it will be interact with there. Those electrons will be interact that sample position, then image will be create. This is SEM. Another advantage is there, if we add a probe of X-ray probe to the SEM, we can call it as EDX. Okay, whatever the elements are there in our sample, that EDX will give by peaks, and where particular peak, carbon peak is there, and then whatever the elements are there in our compound, those will get from the SEM. And TEM is, what is that? Only structural one will give SEM, but we don't know how the intermolecular molecules will be arranged in that. Then TEM will give that, how our nanoparticles, intermoleculars will be arranged in our sample, will give by TEM. And TEM is also same, it will release, source of the TEM is electron gun only. Okay.
So,
thank you.
Thank you, ma'am, for explaining about what is the nanoscience and what is the characteristics of nanoparticles. Now we will go for Naina Vinodini, ma'am. We have so many properties are there in nanomaterials. So, can you explain any important properties of that?
Yes. Definitely. Basically, we look for electrical conductivity in the material and also the optical properties, because bioimaging and sensors are very important applications of nanomaterials. So, definitely we can go for characterization. So far we have learned like what are the nanomaterials and what are the technical methods to synthesize the nanomaterials. Now let us look into the properties, like based on what properties the nanomaterials are classified, like 0 dimension, 1 dimension are. So this is my order, that is nanomaterials and properties, overview of nanomaterials, properties, applications, assaying for nanomaterials. Now what are nanomaterials? So earlier in 10 years ago, so whenever we charge the mobile battery, it would last for only for 2 to 3 hours. But now the battery life is more. And next one is why the sports rockets and bicycles are light in weight, but still they are very strong. And one more, the harmful UV, how we are protecting from harmful UV rays, and what are the medical techniques to identify the diseases at very early stages. So for all these questions, nanotechnology is the answer. Now basically on what properties we would confer, like we will confine the nanomaterials. So basically as madam said, they have to confine to only to the 100 nanometers, and the very property of nanomaterials is high surface to volume ratio, and they show, when they are coming to the nanoscale, they show unique properties of electrical, optical and magnetic properties. So we have seen the synthesis techniques and characterization techniques. Now this is the nanoscale. This is the nanoscale we have seen, that is already madam has explained that what would be the bacteria of the nanomaterial or DNA at what scale, and if you see this tennis ball, it is about 10 power 6 times the nanomaterial there, right. So coming to this nanomaterials, what is the basic difference between nanomaterials and bulk materials? So here the top row is bulk material and the down one is the nanomaterial. So here it is a shape, we have bulk has a different shape and volume, and this is optical. Say even so, as these nanoparticles, they do have quantum dots, they have a rod type, there have cone type, and there are spherical, there are octahedron, all those shapes they will have. And coming to this optical, and when they are in bulk stage, light cannot pass through the bulk materials, whereas when they come to the nanoscale, what they become transparent. I think ladies will not buy if they look at this nanoscale, because they are fascinated about the gold and silver, but when they come to nanoscale, they will not appear as the same as in bulk material. Now very important property is the electrical property, that is the electronic property. We know the valence band and conduction band. In bulk material, the valence band and conduction band are continuous process. That means there is no separation between energy levels. Energy levels are continuous, whereas when they come to nano level, they are discrete energy levels. So the very property is quantum confinement, that I will explain in the later slides. Now coming to the magnetic properties, here you can see the bulk magnetic domain, whereas this same bulk magnetic domain is divided into so many nanoparticles. So they are occupying so much of space, increasing the magnetic ability or attracting power for nanomaterials. So coming to the last, that is the mechanical. We know the diamond is strong, like very strong, and we cannot divide it into. That's it. Even better strength we can see in nanomaterials because of that grain boundaries. So coming to the nanomaterials, as madam rightly said, it is a 0 dimensional, which is called as quantum dot, because 0 dimensions, that is less than 20 nanometers, can be called as, in all 3 axes I can say, as called as a 0 dimensional or quantum dot. 1 dimensional is assuming at x axis, y axis or z axis only along 1 dimension, and 1 dimension మీద మాత్రమే less than 100 nanometers ఉండడానికి ఉంటే దాన్ని అప్పుడు మనం 1 dimension అంటాం లేదా నానో వైర్ అని అంటాం. 2 dimensional అన్నప్పుడు we can say that x and y axis under any 2 dimensions has less than 100 nanometers, then we call it as 2 dimensional. And so as a 3 dimensional, we know it almost comes to the bulk, like it's small, all the 3 sides we have almost 100 nanometers. Now coming to the advantages, why we have to go for nano sized or quantum regime. So very thing is large surface area. When it is bulk, it is occupying a very small portion of area or volume, but when the same bulk material is made into nanoparticles and it is spread over the surface, it occupies more volume, more surface area. So the same volume is converted into more surface area. That's a very property of the nanomaterials. Now, yeah. And we can see this catalysis or sensor applications for this advantage of quantum regime. Coming to the ability of wearing them. Now when they have brought to the quantum level, or rather nano level, the properties are shown in different way, like the bulk is a different property, and at nano level they have a different property. We can see the magnetization, optical properties, melting point, and even hardness, etc., and even relative to that, and without changing the chemical composition. So only when it is turned to the bulk to the nano level, it is converted, the properties are different. Now the why, what is the thing happening there in the material? So here that is quantum confinement, in the sense earlier the electron is continuous process, so but it is confined only to the limited portion, so that it is, we are having a fixed values there. So because we are having the fixed values, we are having discrete energy levels. That is what is the basic thing in the synthesis of quantum confinement or quantum nanomaterials. Next is increased surface to volume ratio. That is, as I already told, the same volume occupying a small portion that is made into nanopowder, which can spread into so much of surface, so that a significantly higher percentage of atoms, because earlier in the same body atoms అన్ని లోపల ఉన్నాయి, కానీ ఇప్పుడు ఆ atoms అన్ని బయటకు వచ్చేసి సర్ఫేస్ మీద స్ప్రెడ్ అయింది కాబట్టి రియాక్టింగ్ పవర్ ఈజ్ మోర్ అని మనం ఫర్ నానోమెటీరియల్స్, దట్స్ బేసిక్ అడ్వాంటేజ్. కమింగ్ టు ద ప్రాపర్టీస్, దీస్ ఆర్ ద ప్రాపర్టీస్ ఐ am going to discuss: mechanical properties, thermal properties, electrical properties, magnetic properties, chemical properties, optical properties, and finally I'll conclude with the structure of materials. So mechanical properties, we know ఎంత టెన్షన్ బేర్ చేయగలదు, లేదా ఎంత కంప్రెషన్ బేర్ చేయగలదు, ఎంత బెండింగ్ మనకి వేర్ చేయగలదు అన్నది మనం మెకానికల్ ప్రాపర్టీస్లో చూస్తామన్నమాట. వాట్స్ ద ఫస్ట్ ప్రాపర్టీ? టెన్సైల్ స్ట్రెంగ్త్. సో ఎబిలిటీ ఆఫ్ ద మెటీరియల్ టు విచ్ ఎంత లోడ్ బేర్ చేస్తుంది అన్నది మనం చూస్తాం. సో హయ్యర్ టెన్సైల్ అండ్ compressive strength ni nanoparticle can bear. So example is because of less structural defects, because in the formation of crystal structure defects are very very less. Defects less kabatti ఏమవుతుందంటే అక్కడ ఎక్కువ atoms ఉంటాయి కాబట్టి ఎక్కువ లోడ్ బేర్ చేయడానికి ఛాన్స్ ఉంది. సో దట్ ఈస్ వాట్ ఈస్ లెస్ స్ట్రక్చరల్ డిఫెక్ట్స్. అండ్ ఎగ్జాంపుల్స్ ఆర్ carbon nanotubes can bear from 50 to 100 gigapascals, whereas manchi steel, higher quality of steel kuda, it can bear up to 400 megapascals to 2000 megapascals. See the comparison, 400 megapascals nunchi 2000 megapascals ekkada, 50 to 100 gigapascals ante 10 to the power of 6 times మనం దాన్ని ఎక్కువగా చెప్పచ్చు. Now coming to the hardness, so the resistance or scratching, అంటే when the surface is smooth, when the nanoparticles are spread over the surface of the particle, that resistance of scratching means anything, it may fall on the material but still it will have the same surface. So indentation means there is no deformity. And coming to the wear means in a moving particles, when they are moving accordingly, body, so they will have wear and tear. Even that can be restricted in the nanomaterials. So even for bulk modulus, much harder than the conventional materials. So what's the reason there? So increased grain boundaries prevent dislocation of the moment. So because though it is subjected to the external load, still it can withstand that, the plainness of the surface. So that is why it is called as the cutting tools. These cutting tools even is used in medicine, and big machines, or the same thing can be used. So here the scratch resistance, we know the surface is scratch proof, like that we will get. So all those are used as nanomaterials are used as the resistant coatings, or protective films, like that. Okay, so that is a hardness property, mechanical property. Coming to the elasticity and ductility, we know elasticity means when the load is there on the load is falling on the material. So though there is a deformity, but still it can get back to its natural original shape and size. So that's the elasticity. So it has a better elasticity than the counterpart of bulk material. And coming to ductility, that is the drawing of material into thin wires. So that ductility property is also shown for nanomaterial property very efficiently with a high quality of this, high ductility, good ductility. So what is that reason there? So high surface energy and grain size. Again, the example is carbon nanotubes. Now coming to the mechanical properties, the toughness. So what is the toughness there? The ability to absorb energy before fracture means any material, if it is subjected to continuous load, there will be a fracture in that. So but that fracture can be reduced. I cannot say that nanomaterial can self heal that fracture, but still the growth of the fracture is very, very less. So that's the advantage of using nanomaterials. So reduced crystal defects, again the same thing, when during the formation of crystal, reduced crystal defects, we can get the smooth surface, rather toughness of the thing. Now coming to this wear resistance, the wear resistance is again in the moving parts. If the nanomaterial is used as a powder, then that can withstand it gives the life to the machine part, because though it is moving, it gives the extra life rather, I should say, extra life to the moving part, because it resists the wear resistance. That is the basic property for the mechanical properties. And the future fracture toughness, this is also one of the important concept in mechanical properties of the properties. So resist crack growth. As earlier I said that though when a material is subjected to continuous load, there is a possibility of having a crack in that material. Okay. But that can be slow down when we are using the nanomaterial. So why are nanomaterials stronger? So as I said, basically it depends on the grain size, that is a particle size, which is characterized by the SEM or TEM, and high density grain boundaries, that is also a SEM and TEM image only, and crystal defects means reduced crystal defect. That's the main part of the thing, because that helps the quantum confinement. Now coming to restricted moment of dislocation means though it is subjected to the extra load, but still it is not dislocated, the atom is not dislocated, and high surface energy. Now what are the applications of these mechanical properties? Let us see that aerospace structures and automobile components, as I said, moving parts, and it is a sports equipment and medical implants, because medical implants when they are placed in the body, they should not lose their shape and they should not lose their property. So okay. That also can be done using this the properties of the nanomaterials, okay. Mechanical properties, okay. I can say. Now even then protective coatings also for certain things we need to have some film like, okay. So that film also can be done. Now finally that is nanoelectronics, right? Okay. Right. Coming to this thermal properties is also a major thing. The very properties are specific heat, thermal conductivity, thermal resistance, and thermal diffusivity. We know the basic definitions of specific heat and thermal conductivity. So it takes less. We can instead of describing, I thought I would take some examples here, and examples are graphene, carbon nanotubes, nanofluids, nanocrystalline metals, and silica nanomaterials. Okay, so the specific heat is moderate, means when in the bulk state, if it is having low specific heat, now it has raised to the moderate level, so that it can take more heat there. So that's the advantage there. And even CNTs, that is carbon nanotubes, and this is slightly increased. Nanofluids, earlier the specific heat may be huge, but that is also can be varied based on that. So slightly altered. So coming to the thermal conductivity, this is also a very, very important property for thing, because even the stations, I mean space stations and all, we use nanomaterials. There it is directly exposed to the sun, but that can be reduced, making a proper nanomaterial there. So that is the thing, that extreme high, because I have taken certain examples over here. Now coming to the thermal resistance, this is also needed. Why? Because it should not get heated up at certain point for some applications. So that thermal resistance helps the material to not to get heated up there. And finally diffusivity, means fast spreadness. So that also should happen in certain applications. Now coming to this electrical properties, this is a very important concept in nanomaterials. Yes, that is electrical conductivity. We know unless the electron flows, there is no current. The very advantage of having this nanomaterial is, it is a bunch of electrons will move rather than a single electron there. But since many atoms are placed on the surface, bunch of electrons will move from one place to the other place. So the ability of material to conduct the electric current conductivity depends on again this is also depend on the particle size, shape, crystal structure, and even temperature. We know the conductivity is depending on the temperature. Now coming to the reason, electrons, the very basic thing is quantum confinement effect. This is the basic property of the electrical thing. What is this quantum confinement effect? Which is causing the quantum energy is transferred from one portion to other portion of the material. So the electron movement is restricted only to certain portions, means we are deciding the energy levels, we are deciding the values. So that's the reason it is the quantum confinement means it is limited. The borders are the limits are given to a moving electron. So because of that, it is when particle size is reduced, becomes comparable to the electron wavelength, electron motion becomes even more restricted, that discrete energy levels. So what are these effects? This tunable electrical conductivity means whatever we need, we know how to tune the radio. So the same way, even the conductivity also can be tuned from one value to the other value. So change in band gap. In the next slide, I'll explain what is the change in band gap. So the improved electronic performance. So the electrons are moving from one portion to, so it is that level is improved, so that the conductivity is faster. So that is how it goes. And quantum transport, this is very, very important. So instead of a single or few electrons, it is a bunch of electrons moving from one portion to other portion. That is a quantum effect. So electrical properties. So this is what I am explaining about. So this is the bulk thing, nano, these are nano, and here this is valence band and conduction band are continuous. So here I can say smaller, large band gap. If it is a larger particle size, smaller band gap. So I can vary the band gap between the valence band and conduction band by confining the number of electrons. This is also an important point. The number of electrons only to the certain portion, I can have the well-defined energy levels over there. So where are the helpful? That is used in LEDs, that is solar cells, photodetectors, and all these, even transistors, micro transistors. So this is what is an important property, that is electron transport. The ballistic transport, I said more number of electrons are moving from one portion to other portion. So the ballistic transport, electrons travel with minimal scattering. The scattering is very, very less. Why the scattering is very, very less? Because many atoms are formed or placed on the small area. So there is no possibility of moving aside. So that is the reason the minimal scattering is there. And the tunneling, another important property.
Tunneling, yes.
Yeah, tunneling with the quantum mechanical property. That means electrons even can pass through the barrier of the material. That's another advantage of having this. And this can be done. Yeah, this can be done. And nowadays the quantum computing is we are having that research in quantum computing. So this ballistic transport of electrons is the basic reason for this particular thing, ballistic transport. Then electrons tunneling, it may be a tunneling process or it the ballistic transport. Now applications, nanoelectronics, of course, sensors, supercapacitors. What are these supercapacitors? Because of this tunneling of electrons or ballistic transport of electrons, we can store the energy in a limited thing. That is a supercapacitor. Nowadays the battery cars are on roads, so we have to charge the battery very fast, and even the discharge should be slow. So that is how the supercapacitors are designed. So batteries, solar cells and flexible electronics. Coming to magnetic properties, we know the basic properties are ferromagnetic, diamagnetic, paramagnetic, antiferro and ferric. Here surprisingly, those who are not having better attracting power, but when they come to nano level, they'll attract. That magnetizing power is more when we compare to the bulk level. So the application is, we know the ferromagnet is mainly used for permanent storage, that is permanent magnetism, because they show the permanent magnetism. And this is the important property in this magnetic property, that is superparamagnetism. So which helps, the nanoparticle size should be somewhere around 20 to 30 nanometers, and the importance is magnetized in external magnetic field, loose magnetization when that is what is needed, means it's like a switch. Means when the magnetic field is on, it should immediately get magnetized. When the magnetic field is off, it immediately should come back. There should not be any residual magnetism. Okay. So that's the advantage of this superparamagnetism. And coming to this advantage, prevents particle agglomeration. What is this particle agglomeration? I said atoms are spread over the surface and they are occupying, but that may lead to agglomeration, means they are coming very close to it. So it may be, the property may be lost, when the very aspired property may be lost, but still that can be done using this superparamagnetism, and safe for biomedical applications. Now MRI contrast agents, drug delivery, targeted drug delivery, that is nowadays we are using the patches for diabetic patients and all, that is all the targeted drug delivery here. Okay. Now the cancer treatment is also done. Now coming to this magnetic anisotropy, it is another important property of nanomaterials, that is orientation. Anisotropy is nothing but the orientation of the magnetic field. Earlier in the previous slides I have shown the bulk magnet and the nano, bulk domain and the nano domains. Yes. So all those domains, they have to orient themselves to the external field. So that's the reason this magnetic anisotropy is a main property for this, and these are used for hard disk and magnetic memory devices. Now coming to this coercivity, we know that magnetic field has to be zero completely. So when they are synthesizing the nanomaterial, we have in our mind saying that it should get on and it should be get off, like switched off. So it should behave like a switch like. Okay. So in that, the coercivity property also makes an important role in switching on or switching off the magnetic material. Now these nanoparticles are can display superparamagnetism properties. Ekkada ఏ range లో ఉండాలి అని అంటే 1 to 100 nm nanometer range లో ఉన్నట్లయితే అవి ఈజీగా ఉంటాయి. అండ్ nanomaterials are more magnetic, as I said. Yes. Because of the spread of the atoms, more magnetic there, and surprisingly sodium and potassium behaves as paramagnetic at bulk level, but when they go to the nano level, they are ferromagnetic. They show the ferromagnetic nature of the material. So we know that ferrous, cobalt, nickel show ferromagnetic material at bulk, but they'll become superparamagnetic at the nano size. Now coming to this, the magnetic monitoring recording devices, MRI contrast agent, drug delivery and biosensors, ferrofluids, environmental remediation and electromagnetic shielding. Now coming to the optical properties, we know here when they have come to the basic property of light, what is that? Absorption, reflection and transmission, and of course scattering and emission also. So this is the gold level, as madam has told already, that this is the bulk thing, but when they have come to different nano level, they are changing their colors. And here also we can see, if the nanoparticle is less than 20 nanometers, it is a adsorption, means adsorption is a chemical property, and it is more than 100 nanometers means it is a scattering property. And we know, depending on that, see, copper and silicon, they are opaque when in the bulk level, but when they come to the nano level, they are become transparent there. Why? Because of the difference here. I am showing here that is a energy band gap, the varying the energy band gap. So now coming to the another optical properties, that is a quantum confinement effect. It is not only, I said electron is restricted to the small portion. Now that also helps the electrical or electronic property, and also helps the optical property in the case of sensors. In the case of sensors we use, right, this band gap increases, changing the color, and when the band gap is increasing, it indicates change in color. And photoluminescence, we know photoluminescence means if the light is falling on certain material and it reflects back, it emits back with a different wavelength. So that also is nowadays we are seeing on roads, like road separators or the fluorescent colors, the fluorescent materials. So they are based on the property of photoluminescence. Yes, optical properties, that photoluminescence. Now coming to the applications, bioimaging, we know what bioimaging is, means the internal organs are how they are imaged. That is also an important property of optical property of the nanomaterial. And of course LED display in airports, in railway stations, everywhere nowadays, whatever the displaying boards, even the displaying boards are also using that optical property technique of the nanomaterials. So technologies and optical things. See, another thing, quantum dot emit different colors depending on their size. So we know red, blue, green are the basic colors. So if the smaller dots are there, they emit blue light, and if the larger size are there, they emit the red light. So this is another very important property, that is super plasmon resonance, SPR. Basically observed in silver nanoparticles and gold nanoparticles. Free electrons on the surface means three stages like solid, liquid, and gaseous stage. Above the other stage is a plasma. This plasma is observed in optical properties, and this helps to illuminate the light, or UV light rather I should say, for the water treatment and all. Okay. So that the surface plasmon resonance is used to kill the bacteria in the water, right, or to purify the water, or for water treatment. So that is what they are also used in the biosensors, medical diagnostics, and chemical sensing. Now coming to the dielectric property, this is another dielectric property, means we know it's an insulator, but still that can be used as a storage, energy storage method. So ceramics, glass, and polymers, metals, so electrical energy. So even the nanomaterials can show the dielectric properties, means we know the basic properties are dielectric constant and dielectric loss. So energy loss, dielectric constant K value decides like how much energy the capacitor can store, how much energy it can be stored, and the dielectric means higher dielectric constant. So at bulk level it may show this different K value, and at nano level even the K value is increased. So at capacitor, if it is holding 2 volts or 4 volts, when it is transformed to the nano level, it can hold up to 10 times more. That's the advantage of having this. So that is depends on, again this is depends on particle size, frequency, temperature, and material composition. And dielectric loss is the energy loss. Energy loss means it is this should not get lost, the energy should not be lost. So that is what is a basic reason, that is a polarization and frequency dependence. This is what I am showing here as a frequency, the dielectric constant is decreasing, that you can say as frequency is increasing. Coming to the chemical properties, these are the chemical properties, that is chemical reactivity, surface area, catalytic activity, adsorption property, oxidation rate, and surface modification. So when it is bulk, these are the thing, and when the nanomaterial, these are the advantages of having the chemical properties. So what is the advantage? High strength to weight ratio, excellent hardness that we have already seen in mechanical properties, and better wear resistance. Wear resistance are also observed. So limitations, but still we do have limitations in chemical properties. Some nanomaterials are brittle, means they become brittle, means as a bulk they may be hard, but when they come to nanomaterial they may become brittle there. So difficult, expensive because synthesizing a nanomaterial is not that easy. It's an expensive process. So mechanical properties can vary, particle size and characterization requires advanced. So these are the nanostructure, as madam has already told, that it is a 0 dimension, 1 dimension, yes, nanostructured material. Yes, yes. So next is the challenges. What all are the challenges we have in synthesizing or in having the properties? They are the agglomeration. So we should see that more number of atoms should not occupy the same space. They should spread over the surface. That is, what is the surface volume ratio? So that should be taken care. And the stability means it should not oxidize, it should not react with the surroundings. That stability should also be there. And size control, because as I said, when it is quantum dot it has a particular property, when it is a wire it has a particular property. So size control should also be there. And coming to the toxicity, in the process of synthesizing the nanomaterial, there is a possibility of having even toxic nature. So that has to be taken care. These are the challenges. And environmental impact, and definitely they are expensive in nature. Characterization process is also an expensive. Reproducibility is also is a tough task there, and scalability is a thing. Now finally, to future research directions, we are grain synthesis. In our city college we are doing grain synthesis, wonderful results we are getting. Even energy storage also we are doing, but rest of all, medicine and nanoelectronics, electrochemical, environmental applications, smart materials, catalysis, these are the future challenges for us. Means for any researchers, those who want to do research in nanomaterials, they should take care of this, and these are the future goals to reach that. Now let me conclude. Nanotechnology is not just a topic in your syllabus. It is a technology that is already improving our daily lives. As future scientists and engineers, understanding nanomaterials will help you appreciate many of the innovations you see around you.
Thank you, ma'am.
These are the references I've gone into, and thank you very much.
Okay. Thank you very much, ma'am. Both of you coming here to express your about nanomaterials, what you are doing in your labs also, I think so. So first of all, this is the time for concluding. So thank you very much, madam. First of all, I would say thanks to our department, head department of physics, Professor G. Pushpa Chakrapani ma'am, to choose this topic. Nowadays this topic is a very huge research is going on this nanomaterials. So here you explained Naina Vinodini ma'am about mechanical properties and thermal properties and electrical properties. What are the difference between these three? Can you tell me a few minutes?
Mechanical
one or two.
Mechanical is the physical thing we are observing, elasticity and the tensile strength and all. Whereas coming to the optical, it is a light is incidenting on the nanomaterial. So based on the incident light, it may be changing the properties. Okay. And you said, ma'am, thermal, you asked about?
Thermal.
Thermal is very important, ma'am.
Yes.
Why? Because when a nanomaterial is used anywhere, like, it should able to withstand the heat, or it should able to enhance the heat taking, or heat rejection should be fast, like how we see in the Carnot's engine, right? So that's how I cannot compare with Carnot's engine here, but definitely I should take care of the thermodynamical properties of the material. So that is where this nanomaterial plays an important role for this.
Okay, thank you so much, ma'am. Maduri ma'am and Naina Vinodini ma'am.
Thank you for giving me this opportunity.
Yeah, thank you so much.
5 minutes.